All right, welcome to Chapter 12. Chapter 12 is a pretty interesting chapter. We're going to talk about some modern materials. We're going to look at solids especially. There's going to be a separate video you're going to want to watch if you want to see how to solve the like the body-centered cubic and the face-centered cubic unit cell problems. I'm going to mention those in here, and we're going to talk about them kind of in theory at first. But if you actually want to see me work one of those problems, you need to look in the other video. We're also going to get into some discussions about polymers and things like that. So buckle up. It ought to be an interesting set of conversations. All right. So we've talked about liquids, right? Now let's look at the bonding that occurs in solids. There are basically four general types of solids. We have our metallic solids, which are going to share that sea of electrons, those really delocalized electrons. We have ionic solids, which are formed when cations and anions are mutually attracted to each other. Okay, we have covalent network solids, which are solids that are formed by large networks of covalent bonds. So many repeating covalent bonds. Things like graphite is a great example, or diamond is a great example of a covalent network solid. And then we have molecular solids, which are individual molecules that are linked to each other just by van der Waals forces. All right, so those are our four main solids. Now, in crystalline solids, we get really highly regular repeating patterns of arrangement. If we have an amorphous solid like obsidian that we can see down here on the right, we actually characterize that by the lack of order, okay, and how those atoms are arranged. Um, Me personally, I'm partial to the crystalline solids. I think that those are pretty interesting. And so we might look at those a little bit more in depth than the amorphous ones. Now, crystal lattices, which are the individual shapes, okay, that form in these crystals, are really complicated three-dimensional structures. So in order to break them down, we kind of think about them in terms of um, we break the substance down, into just what is the repeating pattern that is present. And when we do that, we can see that, we may have an oblique lattice or a square lattice. We might have an hexagonal lattice. And so by breaking down the crystalline structure, we get a little bit more simple, we'll say, subunit to think about when we're talking about those compounds. Now, the individual shape of the lattice is going to repeat. We call those tiles, and more commonly, we call them unit cells. So when you hear a unit cell, think about this is one singular unit of this solid, whatever that solid is. So that's what a unit cell is. It is a singular unit of the solid. Now, there are a lot of different three-dimensional lattices, but here are the 7 basic types. We have cubic lattices, tetragonal, orthorhombic. We have rhombohedral, which is like the best one to say. We have hexagonal, and then the mono and triclinic shapes. We're going to look at some simple crystal lattices, but those are the 7 basic ones, okay? Now, within each major lattice type, there are additional types that can be generated by where you add an additional lattice point. So if you put the additional lattice point in the center of the unit cell, then we get what's called a body-centered cubic lattice. If you put it on the face, then you have a face-centered cubic lattice. So what I'm talking about there are these little dots right here, right? So if it's in the very center of this three-dimensional cube, then we have a body-centered lattice. If, on the other hand, there is one in each face, right? So that would be a total of 6 on a cube, 6 faces. Then we have a face-centered cubic. If you don't have any additional lattice points, if they're only in the corners, then we call that primitive cubic lattice. And those are, when I said we're going to solve some problems about those are the 3 we're going to look at. Now, if you're drawing a crystal lattice or you're trying to visualize it, you put your atoms in your unit cell, and then the structure of the compound is generated by bonding the atoms across unit cells. So in this specific unit cell, we have 2 atoms, right? We have atom number 1 and we have atom number 2, and they are bonded right there. Now, Once I have the lattice, I make a set of tiles, right? So I repeat this lattice over and over and over and over and over and over. And then I bond across the lattice, right? So I form the bond, and that's where I start to see, in this case, my sheet of carbon. I think this would be a carbon sheet, right? So there we go. Right? And in this case, we get um, a hexagonal shape. So back to our primitive cubic lattice discussion. All right, the closer look at that. When you're visualizing these three identifiers and trying to think like, okay, what am I looking at here? How can I label this? Look at what's in the middle of the picture that they give you. So if there is nothing in the middle and there's nothing in the face, then you have, like the face of the cube, then you have primitive cubic structure. If there is only one atom, and you can see it right there in the very middle of the cube, and then everything else is around it, then you have a body-centered cube. All right. And if you have an atom in the center of every face, so one there, there's one back there, there's this one right here that's on the top, that's in the center of the top. We have this one that's in the center on the side. We have this one that's in the center of the bottom, right? There it is right there. And then actually there would be one you can't see that's back here, that's the center of that back face. That is a face-centered cubic. If you cut the solid along those lattice lines, then we can see these pictures right here. And we're looking at how many atoms are present in the unit cell, right? So in the primitive cubic, we have 1/8 of an atom at all 8 corners. And so we have 1 atom per unit cell, all right? If you have a body-centered cubic structure, you have 1/8 of an atom at all of the corners, and you have 1 atom in the center. So that's 1 and 1, that makes 2. If you have face-centered cubic, then you have 1/8 of the atom in each corner. You have 1/2 of the atom on each face, right? Because when you cut the face, you sever that atom in half. That gives you 1/2 an atom on 6 faces. That's 3. 1/8 of an atom at 8 corners. That's 1. 3 and 1 makes 4 total atoms. And so when we look at the math problems on figuring out or kind of examining those a little closer, those are what we're looking at. Like, where are the atoms located in the unit cell? All right, so that's what we're going to be looking at in the other video. So if that's what you're after, you need to check over there. Now, why can we assume that? Well, we assume that the atoms in a crystal are going to pack together as tightly as possible based on the sizes of the atoms. So if you have a really, really, really big atom and a really, really small atom, well, that's going to actually open up a lot of space in between your lattices or your lattices. If you have roughly the same size atoms, then you can usually pack them a lot closer, all right? So that's kind of the underlying assumption that we're making about those crystal lattices. Now, something that's interesting about packing is if you start to look at metals and you start switching out different metals and packing them together, then you can create an alloy. So an alloy is just a combination of 2 or more metals, or 2 or more elements, the majority of which have to be metals. And that's important because technically steel is an alloy. And in year 1 chemistry, you learn, okay, what's an alloy? Well, it's 2 metals bonded together. Well, okay, yeah, kind of, but not really. Steel is carbon mixed with iron, and obviously carbon is not it's not a metal, and yet steel is considered an alloy of iron. So an alloy is a combination of 2 or more elements where the majority is a metal. When you start to add those second elements or third elements or however many elements you're adding together, like Wood's metal, which has 4 different elements in it, you can tailor some specific properties of your new alloy. So Wood's metal, this table 12.2 has some pretty good some good alloys. So if you've ever seen the fuse plugs like in your car, it has some Wood's metal. It's primarily bismuth, but there's also some lead, there's some tin, there's some cadmium in there. All right. If you look at bronze is mostly copper and tin. Really Important alloy for early civilization. It was so important we named an era after it, right? Like the Bronze Age. Stainless steel, really good for surgical instruments. I have a stainless steel frying pan, which I absolutely love. It is 80.6% iron, a little bit of carbon in there, some chromium, and some nickel, right? You can obviously read the rest, right? So basically, alloys have a primary metal with something else added in that adjusts um, the final chemical properties, right, or physical properties. Now, since we're talking about these cubic lattices or these crystal lattices, we want to look at the two different kinds of alloys that we form. You can form a substitutional alloy, in which case that second element that you put in is going to take the place of some metal atom that was there before. So if we look at 14 karat gold, which is an alloy of silver and gold, some of the gold atoms are replaced by silver atoms. If you have an interstitial alloy, then the lattice of your metal is unchanged, but the second element like fits into the gaps. So that's what steel is. Carbon just kind of fits into the gaps between the iron atoms. Now, since we're talking about metals, we do need to obviously discuss some metallic bonding. All right. And when we look at nonmetals and metalloids, throughout Chem 1 and earlier in AP, we basically talked about nothing but covalent bonding. With metals, though, we are missing a bunch of valence electrons. That's what dearth means. Dearth means like scarcity. And when you want to covalently bond something, you need valence electrons to share, right? Covalent, share the valence electrons. But metals don't have enough valence electrons to go around. So you get these big groups of metals, these crystals, and the electrons are just kind of shared among them. In order to kind of visualize that, we call that the sea of electrons. So we think of a bunch of cations, a bunch of metal nuclei, and they are suspended in their sea of electrons that just kind of float hither and yon. Now, if you want to explain electrical conductivity, this is a really good way to do that, right? If you don't apply an anode and a cathode to the metal, the electrons just roam freely. But the moment you put potential charges there, they can line up and electrons can move back and forth. The ability to be malleable, right? To be able to hammer into thin sheets. Well, since you're just in the sea of electron, if I start hitting you with a mallet, right, those cations can fit between each other and kind of layer out smooth and give me my nice thin sheet. So the sea of electron model is a great way to describe metallic bonding. Now, we have looked at molecular orbitals earlier in the year. Something that's kind of interesting about that sea of electrons is it can kind of disappear the gap between molecular orbitals, and so you get this like continuous band of energy, and that's important for some of the electrical characteristics of metals. It'll also be important when we'll kind of come back to this later in the slides when we talk about semiconductors. Now, ionic solids are an interesting discussion that kind of is tied into this crystal lattice structure, obviously because ionic salts form crystals, and also is, relevant to how our metals are bonding, right? Those cubes of metals with all those electrons, because you have that similar level of organization in your ionic solids. Now, the quintessential crystal, when we talk about a crystal, is an ionic compound, not a metallic compound. And two things that you probably already know about or ionic solids, is they have really high melting and really high boiling points, okay? However, they're also brittle. And the brittleness is easily explained by the fact that there are these cleavage lines, right, between the positive and negative charges. So if you look here in this picture, number 3 there, you can see that you can cleave those salt crystals and get those nice straight edges every time due to some of those repulsive forces based on where the charges are. Now, different sized ions in an ionic compound are going to adjust the distance between, the positive cation and the negative anion, but they're going to align in the same 3 shapes that we saw with the metals: the primitive cubic, the face-centered cubic, and the body-centered cubic. All right. So that's, kind of an interesting thing to think about. It's also important because you may see an ionic compound in one of those body centered cubic or primitive cubic lattice problems. You may see a metallic compound, right? It doesn't really matter there, all right? Now, the third kind of solid that we talked about at the very beginning is the molecular solid. And the molecular solid is just a solid that's governed by van der Waals forces. That's what's holding it together. Um, Keep in mind that the individual unit of these solids are discrete molecules. That's not true in an ionic solid. There is no discrete salt molecule. It's just all salt, right? It's all table salt. It's all NaCl. You can cut it every different which way. As long as you get NaCl, you're good. But in a molecular solid, like the benzene it has its own identity. It's a specific molecule, and you have a bunch of them all together, and that's what's making your solid benzene. All right. The fourth kind was covalent network solids, and covalent network solids are pretty cool. They are slightly more like metals than, say, a molecular solid would be, but they still have those covalent bonds present. They're usually really hard, and they usually have really high melting points. Diamonds are a great example of a CNS, a covalent network solid. Graphite, which is very similar to diamond, right, in that they're both made of carbon, is a great example of a molecular solid. And in the molecular solids, we have much less hardness, right? They're softer, and they're going to have much lower boiling points, or melting points, rather. Also, with a diamond, if you rub a diamond on a surface of like a piece of paper, you might tear the paper. You're definitely not going to leave behind a streak of diamond. But on the other hand, with graphite's so soft that as you rub it across that piece of paper, it leaves behind a nice layer of graphite that's going to look just like that if you could zoom all the way in, where it has these nice hexagonal sheets, right? And that's interesting. Now, somewhere between our covalently bonded nonmetals and our metallically bonded metals are the semiconductors. And if we look at the molecular orbitals between or for a semiconductor, we're going to find that there is this band. And because they're really closely packed, okay, there ends up being this little gap between the anti-bonding molecular orbitals and the bonding molecular orbitals. The gaps are going to range between 0.08 and 3.05 electron volts, all right, and that is equivalent to 7 to about 300 kilojoules per mole. Now, on average, okay, the semiconductors usually end up with 4 valence electrons. They're still going to be able to arrange themselves in those same lattices that we saw earlier, okay? But our inorganic semiconductors are going to have about 4. They're going to average 4 valence electrons. So 3 for gallium, 5 for arsenic, right? There's our average. Now you can mess with a semiconductor. That process is called doping. So if you introduce rather more valence electrons, which would be an N-type dope, or if you did a fewer valence electron dope with P-type, then you can increase the conductivity of your semiconductor. All right. So that's something that we use when we're trying to make these modern materials that we need for things like computers that need, our semiconductors need to have, just a perfect level, a specific level of conductivity. We can dope our semiconducting elements in order to get right there where we need to be. Now, polymers are another modern material, okay? And they usually have really high molecular masses, and they are bonded together in these long sequences, these long chains to make something pretty useful, right? There are a lot of common polymers in table 12.5, some that you might be familiar with, things like nylon, things like polyethylene, which makes plastic, or polystyrene, which makes I'm pretty sure polystyrene is your styrofoam, okay? PVC, right? Polyvinyl chloride. All of those are really common polymers that you might have around your house even. To make a polymer, you're going to take a bunch of pi bonds, a bunch of double bonds that are present in your monomer, and you're going to convert them into sigma bonds or single bonds, and in doing so, form a long chain. So the double bonds end up going away, and you end up with these nice long chains of single bonds. Now, this is straight up organic chemistry, and you're not taking organic chemistry, right? You're taking AP chemistry. But a simple understanding of this is not real complicated. As you build this polymer, right, you're going to change the structure of the molecule, right? The monomer structure is changing. We know that structure and function are related. So since there is a change in the structure of the monomer, the polymer should have different compound or different characteristics, different traits than the monomer does. And we often find that that is true. We always find that that is true. Now, you can make a condensation polymer, in which case you put two things together, and usually water is formed as a byproduct. So in this instance here, we have a copolymer being formed. That's the other name for these, and water is the byproduct. Nylon is a great example of a condensation polymer. Make sure you know that one. Could see it on the AP test. Nylon's a pretty common polymer that they refer to. So in order to make nylon, you take diamine and adipic acid. You mix them together, and you actually, if you want to look up a video of making nylon, it's pretty cool. You put the two together, and they don't, they're both liquids, and they don't mix. They have like a thin like interfacing line. And you stick like a loop down in there right at the interface, and you pull the bottom layer up through the top layer, and as you pull it through, it just becomes a strand. That's how you make nylon 6,6. That's the official name there. So that's pretty interesting stuff. Now, polymers have some specific properties we want to know about. We know that as they interact with each other, they're going to lead to more and more regions of order. And when you start to look at these polymers, as they get bigger and bigger and longer, you see repeating patterns over and over again. And something that we know about crystals is a crystalline structure is a bunch of repeating things, right, over and over again. And so polymers start to end up with some crystalline characteristics. We call it crystallinity. And so, the mechanical strength of a polymer, right, if you're trying to make a strong polymer, relies on this crystallinity in order to function. Now, cross-linking is another way that we can make a polymer stronger. As they are more and more kind of linked together, they are harder and harder to bend and break. So cross-linking would be an example of how you might strengthen a polymer. Great example of cross-linking is rubber. Naturally occurring rubber is way too soft to do anything with. You certainly couldn't make a tire with it. So we vulcanize it. And in vulcanizing, we add sulfur to the rubber, and this is going to cross-link the rubber chains. It makes it a little bit tougher, or a lot tougher. It makes it less likely to break down. And so you take something that's really soft, like natural rubber, and you're able to make something like a tire for a car. The last thing I want to talk about just briefly are nanoparticles, because as we move forward in today's society, we are seeing more and more, kind of exotic modern materials. And nanoparticles are a really good example of this, just really, really, really small particles, okay? And these small particles can be used in semiconductors, okay, in what we call quantum dots. And they can, in this specific instance anyway, they are responsible for the different colors you see in these diodes right here, these little, I guess you would call it an LED light. But really useful, right, if you want to make different colored switches in this case. But nanoparticles have actually been around for a long time. We use finely divided metals in order to make different colors in stained glass. And so, we're taking an ancient technique that they didn't know what they were doing, and we're actually applying it to something a little more modern there. And when we talk about nanoparticles, you can't finish that discussion without at least talking about carbon nanotubes. Nanotubes are like semiconductors made out of carbon, obviously, carbon nanotubes, and you don't have to dope them in order to get them to act like semiconductors. Simply tightening the tube shortens the distance, right? It can affect the semiconducting properties. So there are a lot of really cool applications of chemistry to the modern world. And material scientists are the people who go about engineering these things from the ground up. They make a tremendous amount of money in many cases, and they are, responsible for a lot of the modern advances that we may take for granted. So if you're looking for a career that involves some chemistry, but also is a little bit more in the engineering and physics field, you may look at material scientists. You might end up using some of these things in this video. All right. So go ahead and take a break. In the next video, I'm going to actually work some of those crystal lattice cubics unit cell problems. All right. But that's it for this one. So if you need help, let me know. Shoot me an email and I'll be glad to give you a hand.